Hello. Yeah. So, hello everyone. Welcome to today's live interactive session. So, as you all know, today is the eighth week lecture that we will be covering today. So, today is the eighth week of the lectures, and uh, in the previous class we discussed about consolidation, and then we saw the types of consolidation: primary consolidation, secondary consolidation, and also we solved some problems regarding the calculation of consolidation settlement. After that we solved problems, we understood the one dimensional consolidation equation, we saw what is the coefficient of consolidation, CV, and then we solved some problems where we found out the time required for consolidation, right? Where we related the time factor to the time required of consolidation to the degree of consolidation, right? So we did all these things in the previous class, and we ended the consolidation topic there, correct? So in today's class, what we are going to do is that we are going to basically start a new and very important topic, that is the backbone of soil mechanics. It is nothing but the shear strength of soil, right? So already this has been discussed in your theory classes, right? During the lectures, uh, this has already been discussed. So what we will be doing is that we will be solving some problems. Okay, we will be solving some problems from the shear strength chapter, right? So initially we will be recapitulating a bit, we will be revising a bit about all the basic concepts regarding the shear strength, and after that what we are going to do is that we are going to solve some problems. All right. So during the progress of today's session, if you feel at any point that you are getting lost or you are unable to understand the concept, so please feel free to interrupt me and ask me. I will be more than happy to help you. All right. So as I said, this topic, the shear strength chapter, or this topic, is actually the backbone of soil mechanics, right? So it is a very very important and conceptual uh, topic. So we will be just going just around, just we will be just touching a bit those things, okay, for revision purposes. But I hope that you have gone through the lectures that were given in the class very nicely, and you actually uh, should the go through the standard textbooks also, okay, standard textbooks, and you should go through this chapter very minutely and very slowly and try to understand each and everything. All right, because this is very very important to any geotechnical engineer. All right, so it is very important to us to understand this uh, uh, shear strength chapter. Okay, so slowly let us start slowly everything, so bit by bit. Yeah. So what is shear strength of soil? Okay, what do we understand by shear strength of soil? So the shear strength of a soil mass is the internal resistance per unit area that the soil mass can offer to resist failure and sliding along any failure plane inside it. Okay, so shear strength is the internal resistance per unit area, means it is a stress, right? Like it is type of stress quantity, resistance per unit area, stress quantity that the soil mass resist, to failure. Okay, that means say we have a soil mass, and on that soil mass you are applying some destabilizing force. Okay, in that soil mass what you are doing is that you are applying some destabilizing force. So the destabilizing force, okay, due to the application of the destabilizing force. So by destabilizing force I mean, say you are applying, simple words, you are applying some load over that soil. So what happens, less, initially you put very less load, as little by little you keep on increasing that load. So what will happen, as you apply at the instant you apply the load, the soil is going to give some resistance to that load, right? The soil is going to give some resistance to that load, right? So the maximum value of that resistance, okay, the maximum value of that resistance that we can reach, uh, uh, that is nothing but the shear strength or the shear resistance of the soil. Okay, so generally what happens, generally in a soil mass, generally there is a weak plane. Okay, there is a plane of least strength. Okay, that is the weakest plane. Okay, that is the weakest plane. Along that plane the soil mass actually fails. Along that plane the soil mass actually fails. Okay, so as the soil fails, what happens, there is a tendency of the soil mass to slide along that plane. Okay, slide and fail. That's why it's written here that the resistance quantity is the soil mass can offer to resist failure and sliding along any plane inside it. Okay, any plane means here this plane is nothing but the plane of least strength. That is the plane at which the shear resistance. Okay, the shear resistance. Uh, uh, the shear resistance actually, we will see which plane is that, we will see, because now if I say just in the next point we will see which that plane is. How do we define that plane? That is not the plane of the, if I say, I just made a mistake, I just told you that it is the plane of the minimum shear resistance. That is not true. That is neither the plane of the uh, uh, minimum shear resistance or the maximum shear stress, whatever be it, it is not that. It is a some specific plane. Okay, that failure plane is nothing but a specific plane where the shear stress, okay, the shear stress and the normal stress have a definite, have a typical combination, where when they reach a typical combination where the normal stress and the shear stress on a plane which is a typical, which is a particular combination, at that time what happens, the soil fails. Okay, so that is what we define in the next part. What is that plane? The more column four. So there are many failure criteria. So this is one of the basic or most primitive failure criteria. So the main basic failure criteria of soil mechanics, that is the more column failure criteria. Okay, so the material fails because of a critical combination of shear stress and normal stress, and not from either maximum normal or shear stress. So here, say you have a soil mass. Okay, in this soil mass what you are doing, you are applying some load. Okay, you are applying some load in that soil mass. So the failure in this soil mass will happen along a particular plane. Okay, this is going to be the failure plane. Say this is going to be the failure plane. Now which is going to be this failure plane? This failure plane will be the one where the, say this is the failure plane. Okay, where the shear stress and the normal stress on that failure plane, due to the loading that you are applying, due to the overall loading, what is going to happen? Due to the overall loading, we are going to have normal stresses and shear stresses. We are going to have normal stress and shear stress getting generated, right? due to the normal loading, what is going to happen? Due to the loading on that soil, that in all the places, in various planes, in n number of planes, there are going to be but some shear stresses and some normal stresses are getting generated. Okay, but in the failure plane, what happens? In the failure plane, this normal stress and this shear stress that is acting due to the applied load, that achieves a critical combination. Okay, that is this. The failure shear stress is nothing but the function of normal stress. Okay, so this is what gives us the failure envelope. So if I plot shear stress and say normal stress like this, you will get a failure envelope. So along this failure envelope, along all these values, what will happen? The soil is going to fail. If we have a combination, say here, if then the soil won't fail. But any loading combination where we get where the shear stress and the normal stress gives us a combination which falls on this curve, that will lead to the failure. Okay, so this is nothing but the fail. This is called the failure envelope. Okay, this is called the failure envelope. All right. Okay. So this failure envelope, it is generally seen that failure envelope is it is a curved line. Okay, this failure envelope is a little bit curved. So this non-linear failure criteria was then modified using the Coulomb's theory. It's a linear function of normal stress. Okay, it was then idealized as a linear function. Okay, this linear function. What is the linear function? That linear function is nothing but the failure shear stress is equal to C plus sigma tan phi, where C and phi are the cohesion and the friction angle of the soil. Okay, where C is the cohesion and phi is the angle of internal friction of the soil. Okay, so this was actually derived from the Coulomb's theory. So Coulomb's theory, if you remember your friction chapter, so you had say sliding block here, you had an angle of repose here, like that. So angle of repose is what, where the uh, block just overcomes the friction and just tends to slide, right? So you had weight acting like that, like this. So we had everything, friction acting backwards. So we had normal force acting like this. So from there actually we we came to this term. Okay, we came to this. Okay, this equation is called the Moore-Coulomb failure criteria. Okay, so this linearized version of the original Moore-Coulomb failure envelope, or the original failure envelope, is called the Moore-Coulomb failure criteria. All right. So if you remember from this, from your basic class 9th or 10th, I forgot there, it was taught to us, right? So even in class 2 level, so what is the friction? Frictional force is what? R into mu, right? R is the normal force, right? So normal force, so N into mu, or N is the normal force and mu is the friction angle, the friction ratio. Friction ratio is nothing but tan of the angle of repose. So that angle of repose is nothing but our friction angle here. Okay, so this is how these two things were related in terms of soil and this Coulomb's theory. So we studied the concept of effective stress, right? So effective stress is what? Total stress minus the pore water pressure. So in terms of effective stress, if you write this failure theory can be written as the failure stress equal to at failure the shear stress is equal to C prime plus sigma prime tan pi prime. Okay, and for C prime for standard nucleus silt is 0. Okay, there is no cohesion, that means. So later we will see this is cohesion and all those terms are actually relative term. It depends on how what kind of soil is that and how here are you actually testing the soil. It depends upon that also. These are actually very subjective and very relative terms. You cannot say that clay has C is equal to 0. You will see that normally consolidated clays you can have on testing, you can get C is equal to 0 also. Okay. So this Moore column failure criteria if we plot here, we're getting along the y you are plotting the shear stress and along the x you are plotting the effective normal stress, right? So you are plotting that, and so here you get a straight line, that is the Moore column failure envelope. It makes an intercept here, that will be called the cohesion, and the slope is nothing but the friction angle. All right. So here at the point A, if the shear stress and the effective normal stress at any plane falls below this failure envelope, that is at the point AC, then we can safely say that the soil won't fail. Okay, and if this it reaches the point B here, then it is at failure state, and this C is actually unachievable. We cannot have this stress combinations. Okay. Okay. So see this. So what is this? What is this that we have drawn here? That is nothing but the Mohr circle. Okay, this is nothing but the Mohr circle. Okay. So say you have a soil mass here. Okay, this is a soil mass. We are having a soil mass, and in that soil block, what we are applying? We are applying uh, stresses. Okay, so this sigma 1 is greater than sigma 3. So we will call sigma 1. So this is 2D, two dimensional. So sigma 1 is our major principal stress, and sigma 3 is what? Minor principal stress. Okay, minor principal stress. Okay, so AB is what? This AB plane is nothing but the AB plane, or this CD plane is nothing but the major principal plane, because the major principal stress is acting here, and these planes are the minor principal plane because the minor principal stresses are acting. And this EF plane is nothing but the say the failure plane. Okay, and the failure plane makes an angle theta with the major principal plane. All right. So now how can we represent this in terms of Mohr circle? How can we represent this in terms of Mohr circle? So uh, Mohr circle, actually anything, any angle in physical form, if it is theta, then in Mohr circle we have to represent it as 2 theta. All right. So first let us plot the major principal plane in the Mohr circle, or the major principal stress. So major principal stress is what? Major principal stress is sigma 1. The sigma 1 is in the major principal plane, and so in the major principal makes an angle 0 with itself. So 0 means in the Mohr circle also it will be 2 times 0, that means 0. So this this is nothing but the major principal plane. Okay, okay, is nothing but the, so this is the origin. From here along the x-axis we plot this sigma 1. All right, now what is the angle between the major principal plane and the minor principal plane? It is 90 degree. So what will be the angle between the major principal plane and the minor principal plane in the Mohr circle? Obviously it is going to be 2 into 90 is equal to 180 degree. So here we have this sigma 3 you are plotting here. So sigma 3, so obviously you can see from here, if we this we consider the minor major principal plane, so at 180 degree angle we are getting the minor principal. Done. Now the failure plane is making an angle theta with the major principal plane. So there it will be making twice theta. So same you can see it twice theta. So this will be our major principal. So the failure plane. And you can see this failure plane, the point. Okay, so what we can do, we can draw a circle, more circle here, and if you see here this failure plane, this is actually at this point D, the failure envelope actually makes a tangent. Okay, so if we say that this is the failure envelope, so this failure envelope is actually making a tangent at this point. Okay, this failure envelope actually makes a tangent at this point. Okay, now how we get, so what we do is that generally we do several tests known as the triaxial test. So we'll see this triaxial test the subsequent slides, and from the triaxial set, so we get a number of Mohr circles like this, and then we draw a common tangent to all these circles, and from there actually we can get the failure envelope. Okay, and the intercept with the failure envelope makes is the c. See, there is the equation, it gives us the equation, and the slope gives us the angle of internal friction. Okay, now inclination of the plane caused by the shear. So we already, AB is the major principal plane, CD, AD is the failure plane, EF. So we already saw this. So the angle BAD is equal to twice theta. So is this angle is nothing but twice theta, which also can be written as 90 degree plus phi, or we can, from here we can write theta is equal to the failure is equal to failure plane, you can write 45 plus 5 by 2. Okay, so this is important, you can remember this. Also I am not doing the derivation, so if you assume triangles and all those things and then derive, so we can get the relation between the principal stresses C and phi. Okay, in terms of principal stresses sigma 1 sigma 3, effective principal stresses phi and C, we can get one relation. That relation is given actually here. So this is very important, so please remember this relation. uh, Please remember this relation. Okay, and also remember this term. Okay, 10 square 45 plus 5 by 2. Remember this term, we will be encountering this term in also in the later chapters, mostly in the case of retaining wall. So we will see that earth pressure theories, we will be again encountering this term 10 square 45 plus 5 by 2. Okay. Mm, So now let us come to one of the tests, okay, for determination of the shear strength parameters. Okay, so what are, when I say shear strength parameters, what I mean, determination of Cn phi. Okay, Cn phi. So what are the tests that we can do? Okay, for the determination of Cn phi. So one of the basic tests, okay, one of the most primitive and basic tests is the direct shear test. Okay, so direct shear tests are generally preferred for sandy soils, okay, cohesionless soils. For those purposes, generally direct shear tests are purpose, but we can do that other cases also if we have some pore pressure measuring unit there, so we can do that. Just give me 1 second. Just give me 1 second. Just sort this issue here. So direct shear stress, you can see uh, so what we do is that there is, so if you see this diagram, there are two halves. This is the lower half and this is the upper half. So we we actually predefine the failure plane in this case. Okay, we actually predefine the failure plane, and what we do, we put soil sample here, we put soil sample. Okay, we put soil sample, and what we do, we, so it is nothing but a box, okay, box which is the lower half, upper half. So we fill soil in the box, and then what we do, we shear the means we uh, uh, horizontally we relatively relative horizontal, there is some relative horizontal movement between the upper half and the lower half of the shear box. So due to that, what happens, there is some shearing, okay, shearing in this predefined failure plane. Okay, there is some shearing. So from there, so what we do is we keep on increasing. So the soil is there, okay, soil is there, we have the loading plate here, we have porous stones here and here, and we apply some shear force, okay, and there is a normal force also. So what we do is that we keep on applying some keep applying some shearing force, and slowly we keep on increasing, we keep on uh, sharing the boxes, and then at point comes where the soil totally fails. Okay, and so we note down all the values, so we will see how we are doing that. Yeah, so what we do is that we uh, basically we put the soil in this square box. Okay, so the specimen we put in this box. Okay, this box can be either square or circular. Okay, and the standard size of the specimens are also given here. So what we do, shear force is applied by moving one of the box relative to other. Okay, as I said. Okay, and this stress can be either strain control or stress control. So strain control means what, you are giving some strain. Okay, you are moving the box relative, there is some relative, the relative movement you are making it happen at certain rate. Okay, say 1 mm per second, like that. Okay, for example. And stress control test is what, we're increasing the this shearing force, the force you are increasing little bit, so controlling the stress. So there is strain control test or stress control test. Okay, and from this test, what happens, as I said, you are will get shear stress and shear displacement. Okay, so as the stress progresses, so from zero you are starting, so it will increase and increase, it will reach the peak and then it will fail. So this trend is generally seen for dense sand, and for loose sand generally we see a trend like this. Okay, see a trend like this. Okay, gradual mono increase. Okay, there is no dip. Okay, from the peak there is no dip. And so you can see here for loose sand this is the behavior. Okay, okay, and this one you can say the failure shear stress. So we note down the failure shear stress versus the normal stress. Then again what we do, we increase the normal stress, and again we get one more failure stress. So like this we can get many combinations of failure stresses and normal stresses, and from there what we do, we can plot the points and then get a failure envelope. From there if you get the slope we will get phi, and from there you can get the C value. So okay, like this we generally do it. Alright, and for dense, and you can see there we get the peak one, there are peak two values. So one is the peak value and one is the ultimate value. Okay, you obtain ultimate value. This is the trend in case of dense sand. So in order to get this arm of the curve, we generally have to do strain control test. Okay, so if you do stress control test, generally the soil actually the sample actually uh, uh, stress controller generally is unable to give us this later after the post failure, the post peak region we are unable to obtain if we do stress control test. Okay, but in strain control test we can get the total curve, total failure curve. All right. Okay, so you understood this, right? So what we do, say the normal for normal force, first you fix the normal, this normal force at say 1 kg. Okay, then you keep on noting down the values of shear force and shear displacement. Okay, you keep on noting down the values. So corresponding to one normal force you can get some graph like this, then again you put some, again one, say increase it, then again you will get some graph like this. So you can get various many graphs for many normal forces. Okay, and from there what we do, there we get, from there we can get the, from these graphs we can get this failure stresses, failure shear stress, and the normal force already you know. And from there what we do, finally plot the points and draw the failure envelope. Okay, and from there we can measure the phi and C. Okay, now it is up to you, up to the designer, which value for the dense and which value to choose. Either you want to uh, uh, choose the residual, you want to get the residual C and phi from the residual this shear value, or you want to get the P value. It's up to the designer. All right. So I'm not going into detail all these things because everything has been discussed very clearly in your theory classes. Okay, so you can see here. Okay, see here, this is a typical test result, test graph for a uh, dry sand. For a dry sand you can see that C is 0, C is 0, and we are getting some phi value. We'll have definitely have some phi value, but the C is coming as 0. Okay, so that is what it is. For C, for in situ cemented sand is not equal to 0. Okay, this is one fact, it is given, but generally for dry sand it is 0, C is 0. Now, what are the limitations of direct shear? Okay, the shearing plane may not be the weakest plane. So here, what you are doing? So here, this is the shear box, right? So here you are predefining this failure plane. Okay, from beforehand you are defining this failure plane. Okay, okay, you are predefining this failure plane. So, but this failure plane may not be the weakest plane, right? This may not be the weakest plane, right? And one more limitation is that the stress distribution over the shear surface of the specimen is not. So stress means uh, the soil is sheared along this surface, okay, along this surface, right? So along this surface the shear stress distribution is actually not uniform. It is non-uniform. That is one more limitation. Okay, so to overcome these limitations, what we do, uh, we we can do a more advanced version, advanced test. It is the triaxial test. Okay, triaxial shear test. So in triaxial shear test, there is a cylindrical sample. Okay, there is a cylindrical sample. Okay, there is a cylindrical sample. The soil specimen has a 38 mm dia and 76 mm height. Okay, so L by D ratio is 2, right? So we have a soil specimen 38 mm dia and 76 mm height, and what we do, we apply some confining pressure all around. Confining pressure we apply, and then we apply some deviatoric load, like some loading. Okay, we apply some loading, but vertical loading. So this axial stress that we apply, this is called the deviatoric stress. So this deviatoric stress causes the shear failure. All right. So obviously, obviously all around the soil sample, if you apply equal amount of load, that which is the confining pressure, obviously the soil is not going to fail, right? Obviously it's not going to fail. So there are two steps. We will see in detail what are the steps and all those things. So generally in a triaxial test there are two stages. The first stage is the consolidation stage, and the second is the shearing stage. In the consolidation stage, what we do is that we only apply the in the consolidation state, we just apply the confining pressure. Okay, we apply the confining pressure only. So all around confining pressure we apply. So all around the sample we apply confining pressure. So in that stage the soil does not shear. For shearing to occur, we go to the second stage, that is the shearing stage. In shearing stage we apply some deviatoric. So here we apply some axial stress. This axial stress is called the deviatoric stress. Okay, that axial stress is called the deviatoric stress. So we apply the axial stress. So due to the application of that axial stress, what happens? The shearing occurs. Okay, the application of the deviatoric stress causes the shear failure to occur in the soil sample. Alright. So if I draw, this is the sample. Okay, so first we apply the confining pressure all around. It is same. Okay, same confining pressure you are applying all around, sigma 3. That becomes our minor principal stress. Then what we do, the confining pressure. Then after that we apply the deviatoric stress, that is a sigma t. So what we will be at sigma 1 will be sigma 3 plus sigma t. Okay, so sigma 3 is equal to confining pressure, and sigma 1 is equal to sigma 3 plus sigma t. Okay, so this is the basic arrangement, or basic, this is the basic setup of the triaxial test. Okay, this is the basic setup of the triaxial test. So here you can see the sample is actually kept here, and all around it is sample is actually, see, obviously if you go when you do these tests in your geotechnical test in your geotechnical lab classes, it will be more clearer to you, because it is very difficult to explain here. So I will just go through a bit here so that it's easier when you do the test. Okay, so we have the soil sample. We have a soil sample like this. We have a cylindrical soil sample, and the cylindrical soil sample, we put a membrane over it. We put a rubber membrane around it. Okay, we put a rubber membrane around it. At the top and the bottom, at the top and bottom of the soil sample, what we do, we put some at the top and bottom. At the top and bottom we put some porous stones. Okay, porous stones, so that water can actually come out. So we put some porous stones and a rubber membrane, right? So and then the confining pressure is actually applied all around the sample using water. So what we do is fill water all around the sample, so that water pressure actually applies the confining pressure around the sample. Okay, so and then what happens, then we apply, as I said, in the second stage what we do, we apply some axial load here, and that induces shearing in the sample. So there are various parts. So you can see the axial load is applying through a loading ram. Then we have top cap, porous discs, as I said, rubber specimen enclosed in a rubber membrane, porous disc, sealing ring, pressure gauge. Then water is there to apply the confining pressure. And so uh, there are you can see here this bulb, this valve is actually very important. Okay, these valves are actually very important. So these valves actually allow the pore pressure. Okay, so this controls whether you are allowing the drainage to happen or not through the soil sample. So if those valves are closed, that means what? That means you are not allowing the drainage to happen. So if you are not allowing the drainage to happen, if you are not allowing the drainage to happen, what will happen? Pore pressures are going to get generated in the soil sample, right? Okay, but you are not allowing drainage to happen, so consolidation won't happen. So consolidation also won't happen. But if you open the valve and allow drainage to happen, if you open the valve and allow drainage to happen, what is going to happen? That means you are allowing drainage to happen. That means you are allowing consolidation to happen. Okay, that means you are allowing the pore pressure dissipation to happen. Okay, so this is how these things actually work. Okay. So there are various types of triaxial tests. So one is the UU test, then we have the CU test, and then we have the CD test. Okay, so these are the various types of the test. So one by one now let us see what are these tests. Okay, UU, CU, and CD. So there are much more details of this test in any standard textbook. Okay, I suggest that you please go through those and understand the concept of this test. So right now I won't be going into that much detail. Okay, just we will be briefly discussing those, but I suggest that you go through the lectures, class lectures, and then you please go through the standard textbook, so that this test, the concept of these tests are very clear to you. Okay, so that these concepts are very clear to you. So the first we have the UU test. Okay, so UU test is unconsolidated undrained test. Okay, unconsolidated undrained test. So this defines the two parts. Okay, this defines the two parts of the test. So if you remember, right, what did I say? There are two stages of the test, right? The first stage is the consolidation stage, and the second stage is the shearing stage. Okay, so from there this actually defines the two stages. So The first stage is the unconsolidated. So in UU test, what we are doing is that, so stage 1 is what? Stage 1 is the consolidation stage and second is the sharing stage. So in consolidated stage, what we are having? We are having unconsolidated. So in unconsolidated, so as we are to have unconsolidated, we will have drainage valve as closed. Okay. So what we do? We have the soil sample. We apply the confining pressures all around. We apply the confining pressures. Okay, but here we don't allow the drainage. Okay, first, okay, so generally the first step is the saturation, so you have to saturate. So I am not going into that much detail of the test. So saturation state, you have to apply for back pressure, and there, so you need to 100% you need to saturate the state. Okay, after that you use the consolidation. So in the consolidation stage, what happens? In the UU test, we do not apply the drainage or the release of pore water pressure. Okay, we don't allow drainage. So as we do not allow drainage, uh, so the first stage is known as the unconsolidated is we are not allowing consolidation to happen, right? And then we start the second stage. In the second stage also, what we do, we close the drainage valve. We keep the drainage valve closed. So as we keep the drainage valve closed, what will happen? As there will be shearing, as there will be shearing, uh, pore water pressures will get generated. There will be generation of pore water during the shearing stage also. There will be generation of pore water pressure, right? There will be generation of pore water pressure. Okay, okay, in the second stage also. So now what we do generally what we do in the test, first we fix a first we fix sigma 3 is 1 kg per centimeter square. Then you note the axial deformations with the axial load. So we keep noting these values. So from there we can get one graph. So from here what we can do? From here we can get the failure axial stress to or failure deviatoric stress, deviatoric stress. Okay, deviatoric stress you can get. From there we got the field. So corresponding to sigma 3 equal to 1 kg per centimeter square, you get a particular value of sigma d, deviatoric stress at failure, say 5 kg per centimeter square. Just say for example. So like this for various, then again what you will do, will increase the sigma 3. Say now the sigma 3 is 2. So now again you will getting one more value of sigma d. Okay, so again you will be getting one more value of sigma 3. So in UU test it is seen that it is seen that, say first in your case sigma 3, okay, I will write sigma 3 sigma d sigma 1, like this I will write. So first in case of it was 1, you applied 1 kg per centimeter square, then your sigma d will be say 2, say for example, then sigma 1 is 3, right? Sigma 3 plus sigma d is will give me sigma 1. Then what we do to increase the sigma 3, the confining stress, that time you will see that, the sigma d, that is the deviatoric stress at failure, the deviatoric stress at failure is again coming as same sigma 2. So it will be 4. Again if we increase, again if we see that it is coming as same. So this deviatoric stress will always remain the same. That is, the soil is failing at the same deviatoric stress every time. It is independent of the sigma 3. Why? Because because in the shearing stage is undrained. As the shearing stage is undrained, whatever load you are applying, some amount will be taken by the soil and some amount will be transferred to the water. So the amount of stress that a soil is able to carry on its back, it's obviously every time it's going to remain the same. because the water, as the water is completely saturated, as water is there, water is not allowing the stress to get the effect, the stress to get transferred to the soil. You understand, right? If you remember from the effective stress chapter, this concept of spring and piston, that chapter, if you remember, as you are applying the load, what is happening is that whatever extra load that you are applying, that is directly, that is being transferred to the water. It is the pore pressure. It shows up as the pore pressure. Directly, whatever extra load that you are applying, that beyond a certain point is directly gets developed as the pore pressure. The actual load, that is the soil particles, that the actual, whatever the soil particles, whatever the load that is being transferred, that remains always the same. That's why the soil is, every time that the soil is failing at the same deviatoric stress. Okay, that is the reason the soil is failing at the same deviatoric stress every time. Okay, so now if you want to draw the Mohr circle, we will see that you are getting some circles like these. Okay, and all the circles are going to have the same. So now here I am plotting the total stresses. Okay, so all the circles are going to have the same radius. So now if I want to do the total stress failure envelope, I will get a straight line like this. So here I will get C some particular value, but phi will be 0. This is about total stress. But say you measure the pore water pressure in all these cases. So say you measure the pore water pressure also in all those cases. So when you measure the pore water pressure in all these cases, you will see that you are getting only one uh, failure envelope like this. Some failure envelope we will be getting one value, one more circle, and we will be getting one failure, one line we will be able to draw. So that will give you the phi dash and c dash. But the total stress failure envelope is a straight line parallel to the x-axis. Okay, so this was the UU test. Then we have the CU test. CU test means what? We are allowing consolidation to happen in the first stage. So in the first stage, so in the consolidation stage, your drainage valve is now open, and in the shearing stage, again the drainage valve is closed. So in the first stage, so what we do, apply saturate the soil sample, and then what we do, we apply all around confining pressure, and then we open the draining valve. So as soon as you open the instant you open the drainage valve, what is going to happen? The uh, water is going to start coming out of the soil sample. So we are increasing the confining pressure. You keep on increasing the confining pressure. That means you are keeping on increasing the load, this overall loading, the confining load. And what will happen? The water is going to start on ejaculating out through the drainage valve. So port pressure dissipation start. So what we do, for a particular load, particular confining pressure, we let the consolidation to happen. Then we again increase the load, and then we allow the consolidation to happen. Like this we do. So this is a very long. CU test is very long because this consolidation process takes very time, very much, very lengthy. It's very lengthy. So similar to the consolidation test, here also we allow the consolidation to happen. UU test is very fast. This CU test takes very much time. And which test you should do, it depends upon the engineer, and that engineer should decide, the researcher should decide based on how, where you are going to use the CN5 values, on what conditions you are going to use the CN5 values. Okay, on the basis of that you need to have a judgment. You have to make an engineering judgment what type of test you need to do, whether you want it U test, U test, CD test, what test you need to do, that you need to decide. Okay, generally. Okay, so now next stage is the, as I said, is the shearing stage. So shearing stage, what is that? We close the drainage valve. Now again, you are then applying the deviatory test. You are applying the deviatory test. What is going to happen? Pore water pressures are going to get generated. So what we do, you measure, we have sigma 3, we have sigma d at failure, you will get sigma 1, and we have pore water pressure at failure. Okay, so all these values you can get. The sigma 3, you know, you sigma 3, you note this down, this plus this will give you sigma 1, and also you note down the pore water pressure at failure. After that, what you can do from here, also you can calculate the effective values. Effective values you can find out. Effective values also can, you can find out. So what you can do is that, you can now draw the mode circle. So but now the mode circles will be different from the, so now the mode circle will be something like this. Okay, the size of the mode circles are going to increase. Okay, the size of the mode circles are going to increase. Okay, because the consolidation that you are doing, that also changes the characteristics of the soil, because at different stresses now you will be doing the consolidation, right? Okay, so from here you can draw a fail envelope. So this will be like this, fail envelope. So this will give you C, this will give you 5. So now this is the total stress failure envelope. Now if you want to do the effective stress failure envelope, you plot these values. So it will be something like these like this. So you will get a more like this, some you will get a like this. From here you can get 5 dash and C dash. Okay, this is the effective stress so you can get the total stress envelope or the effective stress envelope. Okay, both you can get. Now one interesting thing is that for normally consolidated soil, we get C is equal to 0. Okay, for normally consolidated soil we get the, you will see that the test gives us C is equal to 0, that is coefficient is equal to 0 for normally consolidated soil. Okay, so now in this U test we can also do for over consolidated soil. So in over consolidated you will see that the pore water pressure that is generated, that pore water pressure generation will be negative. So that if the pore water pressure generation is negative, that means this sigma 3 dash will be higher than sigma 3, sigma 1 dash is higher than sigma 2. That time that thing change, that changes. Okay, so those things I am not going into that detail. Please see the lectures and study textbooks, you will be able to understand this. Okay, now the last test is the CD test. The CD test is nothing but the consolidated drain test. Means in both the first and second stages, what we are doing is that we are allowing the drainage valve to be open. That is, we are allowing the drainage to open. So the consolidation stage also drainage is obviously drainage valve will be open. So that's why we are happening. The consolidation is happening, and then after that we go for the shearing stage. And the shearing stage also what we do, we open the drainage valve and we apply the load. The loading rate has to be such low. Okay, the loading rate in the shearing stage has to be so low that the pore water pressures generally do not develop. Okay, so you need to maintain a very low loading rate. Okay, very low loading rate has to be maintained, so that there is no generation of excess pore water pressure. You are so you are allowing the water, means giving enough time for the water to come out, and in that you are preventing excess pore water pressure to get generated. So that's why the loading rate has to be very slow. So in the CD test, generally the pore water pressures are zero, right? So the total stress values and the effective stress values are same, because the this is zero, the pore water pressures are zero. Okay. Okay, so from here you always get a effective, okay, effective dash this. Hmm. Now from this UU test, if you see here, you are getting a straight line, straight failure envelope like this, right? You are getting a straight failure envelope. That means what? That means this C, the cohesion. So this is the C value, and phi is 0, right? So now what we can do, we can do one more test from here, that is the unconfined compressive test. So unconfined compressive test means you are not applying the sigma 3 value. So if you write the basic equation, what is it? Sigma 3 tens 10 square 45 plus 5 by 2 plus 2ic 10 45 plus 5 by 2, right? So now sigma 1 you are applying, sigma 3 is 0 and phi is 0. Phi, you are saying phi is 0, so it's 2ic. So c is nothing but sigma 1 by 2. And what is sigma 1? Sigma 1 is nothing but the unconfined compressive strength, that is the QU. Okay, so the cohesion or the shear strength is nothing but the QU by 2. QU is the unconfined compressive strength. Okay, so this is one more thing that I wanted to mention. Okay, so leave it. So now let us start solving the problems. Okay, let us start solving some of the basic problems. Okay, so let us see how to do those. Okay, so here is the first problem. Compute the shearing strength of a soil along a horizontal plane at a depth of 5 meter in a deposit of sand having the following properties. Angle of friction is given, diameter is given, G is given. Assume groundwater table at a depth of 2.4 meter from the ground level. So determine change in shear strength if the water table at the ground level. Okay. So what is given is we have this. So we have this is 5 meter. Water table is here. Okay. So now at this point let us find out the Let us find out the normal the no, this effective normal effective stress. Okay, nothing but 2.4 into 17.06 plus 2.6 into the submerged unit weight. So submerged unit weight I can find out, right? So if you do this, you will get the submerged unit weight as uh, okay. So E is unknown, right? So E also you need to find. So to find out E, we can use this dry unit weight value. The dry unit is G comma W by 1 plus E. From here I can get E is equal to 0.546. We put that here, we will get this as 3. Okay. So there you can get the effective stress at 68 point square. Okay. What is shear stress? C plus sigma 5, but C is 0 as it is dry sand, or as it is sand we are saying. Okay, C is 0, so it will be 68.82 square. Now what is the second stage? The second case is that determine the change in shear strength water table adjust the ground level. Okay, in that case this this is going to change. So it is 5 into everything is going to submerge. Yeah, so check all these values. Okay, now we have, so very simple and easy problem, right? Direct problem. Now let us see the next one. Just read the question once and see if you can understand. So a given saturated clay is known to have effective strength parameters of C is equal to 10 and phi is equal to 28. Its sample of this clay was brought to failure quickly, so that no dissipation of pore water pressure could occur at failure. It was known that major principal effective stress was that is pore water pressures are being generated because no dissipation very quickly it was brought to failure, so that no dissipation of pore water pressure could occur, so that there is some, that means there is some pore water pressure that is getting developed. It was known that the major principal effective stress is 60 kPa, minor principal effective stress is 10 kPa, and pore water pressure at failure is 20 kPa. Okay, so let us do this. Estimate the value of major principal stress and minor principal stress at failure. So, okay, major principal effective stress is 60 kPa, minor principal effective stress is 10 kPa. Okay, and pore water pressure at failure is what? 20 kPa. Okay, sigma 1 will be what? Sigma 1 is plus you have something what 80 kPa, and sigma 3 equal to 30 kPa. Right, so this is what, these are the values. So simple, right? Major principal stress and minor principal stress failure. Very simple. Just add the values of the pore water pressure with those of the effective values. We'll get the total values. Right? The next is what was the effective normal stress on the failure plane. So to find out the effective normal stress, we will use this relation. Effective normal stress is nothing but, so these relations and all these things, all these you might have studied in uh, your soil strength, soil mechanics course, right? So what is 90 plus 5? So from here I get theta is equal to 40 plus 5 by 2. 55 plus 28 is the action angle. 59 degrees the horizontal inclination of the what? Of the failure plane with the maximum principal plane. From here I will get this as can get this as 23.6. Okay, this is also very simple, direct. Just you have to use this. First one was extremely simple, just you have to add the values, and with the second case just you have to use this basic relation. Okay. Okay, now let us see the next problem 3. So this is the direct shear test result. Okay, so direct shear test carried out on a sandy clay gave the following results. Vertical load is given and the divisions of Provin ring dial gauge is given. So one division is 1 micrometer. Okay, shear box is 60 mm and 60 mm size. The Provin ring constant is 20 Newton per micrometer. Determine the apparent cohesion and angle of internal friction of this. So we need to determine the apparent cohesion and C and phi values we need to determine. So how will you determine? We have vertical load, vertical loads we have, right? Uh, so vertical loads we have, and from what we can do from this we can get the uh, uh, this failure, what to say, failure shear, shear stresses. So we have the normal stress, shear stress, we will plot them, we will get the failure envelope. The failure envelope we can get C and phi values, right? So let us do that. Very direct and very easy. So load vertical PR providing displacement providing and shear force in Newton. So this value is given, right? 20 Newton per micrometer. So first is 36.8, this is 17. So 17 into 20 will give us the value. So 340 Newton. Okay, this is the shear force value. Then next we have 73.5. Okay, now these values you need to convert to stress values. So shear stress and normal stress. So 340 divided by 60 into 60 square and 36. Similarly, oh, it can be 0.2. Okay, then what you need to do is that you need to plot this values. Yeah, like this you have to. After plotting, please check these values by plotting yourselves in graph paper or whatever you can use Excel also. This is approximately phi is 26.5 degree. C is 14.6 kp. Okay. Let us see the next problem. A standard specimen of cohesionless sand was tested in triaxial compression test and the sample failure at Rebatrix test of 482 kPa. Is the Rebatrix test at failure is given. When the cell pressure was 100 kPa under drained conditions, find the uh, uh, find the effective angle of shearing resistance of sand. What would be the Rebatrix stress and the major principal stress at failure for another identical specimen? Okay, let us first solve the first one. Find the effective angle of shearing resistance when the okay, we need to find the effective angle of shearing resistance, and the conditions are drained condition. Drained condition means what? Drained condition means the pore water pressure is 0. Drain condition means the pore water pressure is 0. Okay, so that we need to solve. I will give you 2 minutes, just try to solve this one. We'll just come just wait. Just I will give you 2 minutes to try to solve this one. Just think, just you, what you need to do is that first try to solve the first part. What we need to do, you need to use the those basic equations. Sigma 1 is equal to sigma 3 10 square 45 plus 5 by 2 plus 2 10 45 plus 5 by 2. That you have to use, and that using that you need to solve. Okay, just try to solve this. So, were you able to solve this? Were you able to solve the first part? It's quite easy. You see, it's quite easy. See, This is totally this is a drained condition problem, right? So totally the condition is drained, which is the effective stress is 0. So this given cell pressure is will be equal to the effective minus is nothing but 100 kPa. Derivative stress is so sigma 1 effective is coming to me. Now if we use cohesionless sand, means this is 0. Sorry. So if you solve this, you will get SS. So we have solved the first part, right? Effective angle we have solved. The second part is what would be the deviating stress in the major principal stresses failure for another identical sediment specimen of sand if it is tested under a cell pressure of 200 kPa. Now cell pressure is increasing. Identical specimen, as soon as we say that the specimen is identical, that means C and 5 values are going to be same. Okay, C and 5 values are going to be same, so C will be 0 and 5 will be same, 44.9. So let us do that. Same problem. Sigma 3 now is 200. So how much will be the sigma 1 at failure? This will come out as 1164. Therefore, the deviating stress now will be, it is right? Okay, quite simple. Just directly you need to use the values and find it out. Now next, two identical soil specimens were tested in a triaxial apparatus. The first specimen failed at a deviating stress of 770 kPa when the cell pressure was 200 kPa. Okay. Two identical soil specimens were tested in a triaxial apparatus. The first specimen failed at a deviating stress of 770 kPa, that is 200, and the second specimen failed at 1370 under cell pressure of 400. Determine the value of C and P identically with the same cell stated direction number. Okay, so that part we will see later. First, let us determine C and phi. Okay, how we get it? What we will do? We have two values, two sets of values. We will have two equations of this basic equation. Then we can solve this to find C and phi. Very simple approach. So 770 plus so this is one, and what will be the second equation? Right. So if you solve this, Okay, now we'll put that. So like this, just simply by solving you can just solve it. Now what is the second part? If the same soil is direction part is normal stress, estimate the shear stress is failure. So for that, what you will do, see, I know normal stress, it's given in the question. Solid KPA. Done. Quite simple. Directly just using the data, we put in the equation, so we found out the value. Okay. Next problem. CD triaxial test was conducted on an NC clay yielding the following data: minor principle. CD means what? Effective, and those things are, everything is effective value. Okay, because border pressure generation is not there. Determine the angle of internal friction. Okay, now if you remember, now if we recall, for a normally consolidated clay, the C value is 0. Okay, the C value is 0 both in CU test and CD test. The C value is 0. Okay, for a normally consolidated clay. That you will use, that fact you are going to use to find out. Sigma 1, C0. From here you will get, and what is the failure plane? Angle which the failure plane means the measured principal axis, the 45 plus I by 2. This one you know already used this relation before. Just plug in the values. Cos to 55.39 to get 332. So these problems are actually very easy, right? These problems are actually very easy. Directly you are just going to use the known relations and put the correct values to find out the results. Okay, if you put the correct values, you can easily find out the results. So this is the normal stress at failure. Therefore, the shear stress at the failure. So what will be the shear stress at the failure plane? Okay, so this is the shear stress at the failure plane. But What is the maximum shear stress that is coming on into the soil sample? What is that? This max is, so from here what you can understand, soil sample fails at a point where the shear stress is not maximum. So at the failure plane the shear stress is this one, 128.54. That means what? The soil sample fails at a plane where the shear stress is not maximum. Rather, it fails at a point where the normal stress and the shear stress attain a critical combination. Okay. So say this is the failure plane like this. Okay. So the so this is my theta. So at this point a critical combination is achieved. Okay, this point the critical combination is achieved. All right, this point sigma nf, and this is our tau f. But what is the maximum? What is the maximum shear strength? Maximum shear strength is this one. It is the radius, nothing but sigma 1 minus sigma 3 by 2. But the soil does not fail at that point. So you should remember the plane of failure is not the plane of maximum shear stress. So the plane of failure is not the plane of maximum shear stress. Okay. Now next problem, a CU triaxial test was conducted on a soil sample with soil pressure 100 kPa. The barometric stress at failure was observed to be 60 kPa. The soil is known to have C is equal to 0, phi is equal to 30 degree, and 100 Cu equal to 0 and phi is equal to 13.3 degrees. Okay. So here you can see the undrained values are given as well as the effective values are given. Okay. So we want to, what was the pore water pressure? So we want to find out what was the pore water pressure at failure. That we want to find out. Okay. So just let us write down the values first. This CU test, right? What will be C1? These are total values, right? 100 plus 60. Okay. Now let us put the values. So if this is, so what is going to be the effective minus the this one pore water pressure failure? Similarly, sorry. Similarly, NSUF. Right. Now, for C is equal to 0, what we can do from that our basic equation, this we can write that only, but rearranging, writing the 10 square 45 plus 5 by 2 is a different form. A different form, what we can write? We can write sine three, and also we have effective. Okay. Okay. Now, if you want to use this, right? From here I can write NSUF. Isn't it? So Here you cancel 160, 160 minus 160, 60, so 120, right? So 160 minus 60 is equal to 120 is equal to 260 minus 2 UF. From here I can get F is equal to 260 minus 120 by 2, think but 70. Okay, so that's how we can calculate. Okay, now if you are wondering from where we got this relation, this is nothing but the, okay, this came from our basic equation. So basic equation was what? Sigma 1 is equal to sigma 3 10 square 45 plus 5 by 2, and twice c something something something. So if c is equal to 0, so only we have this part. From here I can write sigma 1 by sigma 3 is equal to what? 10 square 45 plus 5 by 2. So this 10 square 45 plus 5 by 2, in other form I can write it as 1 plus sine phi. So this is how we get from here. Here if we on rearranging we can get this. Okay, on rearranging we can get this. That's all. Just a different form. A different form we are writing that. Okay. All right. Very easy. Next problem, the effective shear strength parameters of a completely saturated clay are C prime is equal to 20 kPa, 28 degrees. A sample of this clay was tested in a UU test under cell pressure of 180 kPa, and a deviatoric stress at failure was 100 kPa. What was the value of the pore water pressure at failure? Okay, so this effective stress parameters are given, and we need to find out the value of the pore pressure at failure, pore water pressure at failure, that we need to find out. So let us do, so let us just write the values first. So C prime is 20, prime is 28, sigma C is equal to sigma 3, UU test, right? So sigma 1 was nothing but sigma t plus sigma 3, 100 plus 180, 280 kPa. Alright, now we will use the again the basic equation in terms of effective. We write in terms of the effective stresses. So sigma 1 is 280, so 280 minus done. All values you know except just you need to find out. If you solve this, you will get u at simple. It is simple. All the values you know, you put in the correct equation, in the correct form, you will get the answer. Right? Just straightforward, very simple. Nothing much to do. Right? Nothing much to do. Now let us go to the next one. That is also similar. The results obtained from a series of CU tests on a soil uh, give the following results. Okay, the results obtained from a series of CU tests on soil give the following result. C CU, C prime is 0, pi CU is equal to 17 degrees, and pi dash effective is 32 degree. If the soil sample was status is under cell pressure of 180, determine the David-Frick stress at failure, pore water pressure at failure, measurement is okay. So one by one, let us find. First, let find out David-Frick stress at failure. Use the same pattern, same thing. Just use the same thing. Just calculate. Try to do it by yourself. Just same thing, exactly the same way. You need to use the basic equation, plug in the correct values, and find the value. Just try to do it. Just use the same equation, plug in the correct values, and try to find out the David-Frick stress at failure. Just try. Are you able to do it? See, all values are given. Just you have to put the values in this equation. Okay, C is given as 0, right? Just put the other values. So sigma 1 you don't know, sigma 3 you know, cell pressure is 180. The total values you have to put, right? 17, because C is 0. Why total stress values? Don't confuse and put this effective stress values here, because see, this cell pressure, whatever value is given, this is the total value, right? Not the effective value, because it is given cell pressure. This is the total value. So just find this out, calculate this. It will be 328.74. Therefore, weighting stress is sigma 1 minus sigma 3. So 328.74 minus sigma 3 is 180. So this will be 140.4 kb. Now next is pore water pressure at failure. So find this out. Same to this. Just here now you need to use the effective values. So sigma 1 dash is equal to dash by 2. So this is what sigma 1 minus u, sigma 3 minus u. Put the value 328. Calculate the u from this. It will come out as What is the third one? Major principal effective stress is failure, nothing but simple and minor. You see only 180 minus. Right? Very simple. Similarly, solve this problem. When an unconfined compressive compression test was conducted on a cylindrical soil sample, it failed under an axial stress of 120. So remember what I said, how to relate C and UCS value, but how to relate cohesion or shear strength in terms of unconfined compressive strength. Use that fact and solve this. Try to use that and try to solve this, please. So here that you cannot use directly because this has some phi value. Okay, there is some C and phi value, so directly you cannot have C is equal to uh, Q by 2 or C is equal to sigma 1 by 2. That you cannot use here because it has some C phi value here. If phi is 0, then you can write C is equal to sigma 1 by 2 or C is equal to Q by 2, but that you cannot do here. Okay. So theoretic stress is the at failure is 120, axial stress at failure is 120. Theta failure plane makes 50 degrees with the horizontal. This is a major principle. So from here I can write. So here phi will be what 10 degrees. Now so now in UCS test, in unconfined compressive test, what is the thing? In unconfined compressive test, this is there is no confined pressure, so this is 0. So directly C is 5. That is what I said. If phi would have been 0, then it is nothing but sigma 1 by 2 directly. But if you have some small value of phi, then this will be the C value. This is phi. So sigma 1 is what? Sigma d plus sigma 3. So 120 plus 0, 20. So you get CS 34.3. No, 34, sorry. You get CS, let's put it down, 50.35. Okay. Next problem, in an unconfined compressive test, a sample of clay 100 mm long till 100 mm long and 50 mm in dia falls under a load of 150 Newton at 10% strain. Calculate the shearing resistance. Okay, the effect of cross section. So for that, see, this strain is given 10%. Okay, that is 0.1. Now corrected area is 1 minus pi L. So N0 is 5 by 4 into 50 square, 0.1, nothing but 21.2 square. Now what is UCS of clay? Perfect clay 50. We'll consider 50. So UCS is what? This is QU is 150 divided by area. Area is 21.82. That will give us the unconfined compressive strength, because it is the failure load divided by the UCS area will give us the UCS. Understood, right? So this is the failure area and this is the failure load. So failure load divided by the area will give us the UCS value, unconfined compressive strength. Okay, the stress value, right? Now what is asked? Calculate the shearing resistance. So shearing resistance is what? This is the shearing resistance. What? Phi is 0. So this is equal to C. And C is what? C is equal to, as you know, QU by 2. So this will be 34.35 kilonewton per meter square. Okay. So this is how we do it. Now last problem. Lab results on a soil have shown that UCS is 120 kPa. In a triaxial test, a specimen of the soil, when subjected to a chamber pressure, that is the confining pressure of 40 kPa, failed at an additional stress of 160 kPa. That is the revertic stress, additional stress 160 kPa. They estimate the shearing strength of the same soil along horizontal plate at depth of 4 meter in a deposit. Okay, the soil properties are given. The index properties of the soil are given. First, what shall we do? We shall find out the CN phi value. CN phi, let us find out. So QU is PA, confining is nothing but 3, is 40 kPa, and deviatoric is 60. Now sigma 1 as usual. For UCS, sigma 3 is 0. We know that, so we can write 120 is equal to 2IC10. Let us give this equation 1. Now for the second case, now, so this one we did, this equation we wrote for the UCS. Now let us write the equations for the triaxial test. For triaxial test, let us write down. So 40 plus 160, this sigma 3 plus sigma d, is sigma 1. Plus this 2IC 1045 plus 5 by 2, we can write from equation 1 is 120. From equation 1, from here we can write 2 is equal to so 5 can get us. So I got the phi value. Now next is C value. Just you will substitute this phi in equation 1. So we'll get C value. C is 120 by just calculate this 120 by, so just putting this in here, okay, this in this equation, we'll get the C value. will come out as 42.26. Okay, done. The CN5 found out. Now estimate the shearing the same soil along horizontal depth of 4 meter in a deposit. Okay, so we have something like this, 4 meter, and 2.5 meter here we have water table. So dye density is given as 17, the G is 2.7. Okay, so from here I can find a ES G gamma W gamma D minus 1, 2.7 into 9.1 1, so 0.558. Submerged will be G minus 1 by 1 plus E gamma W. This will be 2.7 minus 1 by 1.558. 1, this is going to come out as 10.7. Okay, for the effective stress at this level is what 2.5 into 17 plus 1.5 into 10.7 square. Okay, 5. Just put value, C value was 42.426, 42.43 plus 2, how much? 10, 19.4, get 63.5. So this is the yes. All right, so with this we end today's session. I hope all the problems were clear, and if you have any doubts, please feel free to message me or mail me anytime. I will be more than happy to help you. Try to solve all these problems again by yourselves. Read a standard textbook, everything. Read this chapter very carefully. Read each and everything very carefully. Read any standard textbook, okay, any standard textbook, everything very carefully. Read about the triaxial test very carefully. All right, read about the triaxial test very carefully, okay, and solve these problems one again. Practice these problems once again, okay, then all concepts will be clear. So thank you for attending today's session, and next we will be meeting on 22nd of March, that is next Friday, same time from 6 p.m. to 8 p.m. 22nd of March, let us meet on next Friday. All right, uh, so thank you so much for attending today's session, and stay well, stay healthy, and let us meet on the 22nd at the same time. Okay, so please attend the session. So as you can see, if we solve the problems and if we discuss all these things, everything like the concepts will get clearer to you. All right, okay, so let us with this thought, let us end today's session, and thank you so much for attending. See you in the next class on 22nd March. Okay, 6 p.m. to 8 p.m. Thank you.